The idea that one could go right round the universe and end up where one started makes good science fiction. But it doesn't have much practical significance because it can be shown that the universe would collapse to zero size before one could get round. You'd need to travel faster than light in order to end up where you started before the universe came to an end, and that is not allowed. In the first kind of Friedmann model, which expands and recollapses, space is bent in on itself, like the surface of the Earth. It is therefore finite in extent. In the second kind of model, which expands forever, space is bent the other way, like the surface of a saddle. So in this case, space is infinite. Finally, in the third kind of Friedmann model, with just the critical rate of expansion, space is flat, and therefore is also infinite. But which Friedmann model describes our universe? Will the universe eventually stop expanding and start contracting, or will it expand forever? To answer this question, we need to know the present rate of expansion of the universe and its present average density. If the density is less than a certain critical value, determined by the rate of expansion, the gravitational attraction will be too weak to hold the expansion. If the density is greater than the critical value, gravity will stop the expansion at some time in the future and cause the universe to recollapse. We can determine the present rate of expansion by measuring the velocities at which other galaxies are moving away from us, using the Doppler effect. This can be done very accurately. However, the distances to the galaxies are not very well known because we can only measure them indirectly. So all we know is that the universe is expanding by between 5 and 10% every 1,000 million years. However, our uncertainty about the present average density of the universe is even greater. If we add up the masses of all the stars that we can see in our galaxy and other galaxies, the total is less than 1/100th of the amount required to halt the expansion of the universe, even for the lowest estimate of the rate of expansion. Our galaxy and other galaxies, however, must contain a large amount of dark matter that we cannot see directly, but which we know must be there because of the influence of its gravitational attraction on the orbits of stars and the galaxies. Moreover, most galaxies are found in clusters, and we can similarly infer the presence of yet more dark matter in between the galaxies in these clusters by its effect on the motion of the galaxies. When we add up all this dark matter, we still get only about 1/10 of the amount required to halt the expansion. However, we cannot exclude the possibility that there might be some other form of matter distributed almost uniformly throughout the universe that we have not yet detected, and that might still raise the average density of the universe up to the critical value needed to halt the expansion. All of the Friedmann solutions have the feature that at some time in the past, between 10 and 20,000 million years ago, the distance between neighboring galaxies must have been zero. At that time, which we call the Big Bang, the density of the universe and the curvature of space-time would have been infinite. Because mathematics cannot really handle infinite numbers, this means that the general theory of relativity on which Friedmann's solutions are based predicts that there is a point in the universe where the theory itself breaks down. Such a point is an example of what mathematicians call a singularity. In fact, all our theories of science are formulated on the assumption that space-time is smooth and nearly flat. So they break down at the Big Bang singularity, where the curvature of space-time is infinite. This means that even if there were events before the Big Bang, one couldn't use them to determine what would happen afterward because predictability would break down at the Big Bang. Correspondingly, if, as is the case, we know only what has happened since the Big Bang, we could not determine what happened beforehand. As far as we are concerned, events before the Big Bang can have no consequences, so they should not form part of a scientific model of the universe. We should therefore cut them out of the model and say that time had a beginning at the Big Bang. Many people don't like the idea that time has a beginning, probably because it smacks of divine intervention. The Catholic Church, on the other hand, seized on the Big Bang model and in 1951 officially pronounced it to be in accordance with the Bible. There were, therefore, a number of attempts to avoid the conclusion that there had been a Big Bang. The proposal that gained widest support was called the steady-state theory. It was suggested in 1948 by two refugees from Nazi-occupied Austria, Hermann Bondi and Thomas Gold, together with a Briton, Fred Hoyle, who had worked with them on the development of radar during the war. The idea was that as the galaxies moved away from each other, new galaxies were continually forming in the gaps in between